Today's outcome is I can relate observable phenomena to the behavior of gases. So for your drill, if a gas is compressed from 4 liters to 1 liter and the temperature remains constant, what happens to the pressure? So go ahead and pause the video and come up with your prediction for how the pressure is going to change. When you're ready, you can press play again. So we're taking the volume down by 1/4. We're going from 4 liters down to 1 liter. So volume and pressure are inversely related, and the inverse of 1/4 is just 4. So we can conclude that the pressure is going to increase by 4 times, by a factor of 4. So we're going to be working on classwork 3, which is gas law demos. So the vapor pressure is a measure of the force exerted by a gas above a liquid. So if I have a liquid sitting in a beaker, some of those liquid molecules are going to evaporate and exist as a gas above the liquid. So that gas above the liquid is going to exert a pressure, and we call that vapor pressure. So we can measure the vapor pressure of a liquid using a manometer. So this U-shaped device has one end that is open to a sample of gas, and the other end is open to the atmosphere. So if the vapor pressure of the liquid is greater than the pressure of the atmosphere, it forces the mercury up the tube. So the bigger that, the harder that gas is pressing, the more it's going to displace the mercury up the tube. So we can measure the difference between the level of mercury, and that's what we see here on our diagram. So this is the difference in pressure between the gas that's in the flask versus the pressure of the atmosphere. So which image shows the pressure inside the flask being equal to the pressure of the atmosphere? And how do you know? And comparing these two samples, which one shows the greater vapor pressure? So you can go ahead and pause this video and work on these questions right now. So the air at 0 degrees is showing equal pressure to the atmosphere, and that's because the mercury levels that we see here are equal. So that means that the air in this flask is pushing on the mercury equally as hard as the atmosphere is pushing on the mercury. So which one shows a greater vapor pressure? That's going to be the ethanol at 20 degrees Celsius. And we know that because the mercury has been displaced further. Now this makes sense because when the liquid is at a higher temperature, more of those liquid particles are going to evaporate into a gas. So we'll have more gas above the liquid, which means a greater vapor pressure. So if the atmospheric pressure is 7.61.0 millimeters of mercury, what is the pressure of our two vapor pressure of our two solutions here, ethanol at 0 and ethanol at 20. So pause this video and go ahead and see if you can come up with the solution here. So at 0 degrees, the ethanol gas is pushing harder than the atmosphere by 12.2 millimeters of mercury. So that must mean that the pressure of the ethanol gas is greater than the pressure of the atmosphere by 12.2. So we would add 12.2 here. For the ethanol gas at 20, it's pushing harder by 43.9 millimeters of mercury. So the pressure of the ethanol must be 804.9 millimeters of mercury. If the atmosphere was pushing harder, then we would need to subtract instead of add like we did here. Now, pressure is measured in several units. So we've looked at millimeters of mercury, but we also have kilopascals and atmospheres, ATM. So these are the conversion factors here. 101.3 kPa is equal to 1 atm, which is equal to 760 millimeters of mercury. So go ahead and try number 4 and 5 using dimensional analysis to convert units here. Okay, so the vapor pressure of the ethanol at 0 degrees was 773.2 millimeters of mercury. So I'm going to put millimeters of mercury on bottom to cancel, and we're solving for kPa. So I'm going to go ahead and fill in my values here. 101.3 kPa is equal to 760 millimeters of mercury. So when I solve, units of millimeters of mercury will cancel, and I'll get units of kPa in my answer. In number 5, we're starting with 804.9 millimeters of mercury, and we want to convert this from millimeters of mercury into atmospheres. So 1 atmosphere is equal to 760 millimeters of mercury. So when I solve here, I get 1.059 atm. For a liquid to become a vapor, in other words, for it to boil, the molecules must have enough kinetic energy to escape the attractive intermolecular forces between the liquid particles. So in order to boil, the pressure of the vapor must be equal to the pressure of the atmosphere. So usually this means that I have to heat the liquid until that vapor pressure is high enough to match the pressure of the atmosphere, at which point it will boil. So in this diagram here, notice that we have evaporation and boiling. And the difference here is that in boiling, the vapor pressure of the liquid is the same as the atmospheric pressure, so we get these bubbles present in solution. In evaporation, we don't see bubbles occurring, and that's because the vapor pressure is less than the atmospheric pressure. So to get a liquid to boil, we usually add heat to it until the vapor pressure of the liquid is the same as the vapor pressure of the atmosphere. So the relationship between vapor pressure, temperature, and strength of intermolecular forces. Take a few minutes to think about this and write down your response. So as temperature increases, the intermolecular forces in a liquid are going to be weakened. So that will mean that more particles are able to escape the liquid and become a gas. So if more gas particles are present above a liquid, the vapor pressure is going to increase. So whenever we heat a liquid in order to boil it, we're trying to help more of those particles be able to escape the liquid and become a gas so that the vapor pressure is equal to the pressure of the atmosphere. Now, the image below is showing water at different temperatures at sea level and on top of Mount Everest. So take a moment to pause and work on this question. So in order to boil, the pressure of the atmosphere must equal the vapor pressure above the liquid. So at sea level, at 70 degrees, the atmospheric pressure is greater than the vapor pressure. So the vapor pressure is less than atmospheric pressure. So at 70 degrees, water doesn't boil at sea level. But if you raise the temperature of the water up to 100 degrees, now that atmospheric pressure is equal to the pressure of the vapor, and now we have boiling. Now, on top of Mount Everest, the atmospheric pressure is about 1/3 of what it is at sea level. So you've heard before that the air gets thinner as you go up. There's literally less particles of air on top of Mount Everest. So the pressure of the atmosphere is much lower on top of Mount Everest. That's because at sea level, you have more of the atmosphere on top of you than you do at the top of Mount Everest. So because the atmospheric pressure is lower on Mount Everest, I'm able to get that vapor pressure matching the atmospheric pressure at a much lower temperature. So here's a demonstration called boiling in a vacuum. And what we're going to do here is we're going to observe some cool water being placed in a vacuum jar. So this is a container that will suck out all of the air in the jar, and it's going to reduce the atmospheric pressure inside the jar. So the water is going to be able to boil here at a significantly lower temperature.
In this demonstration, I am taking water that's in a beaker, and it has a thermometer in it, and it's going to be placed in something called a vacuum chamber. So as I pan back out here, you're going to see that I've connected that apparatus to a vacuum pump, which is going to pump out the air molecules. Avogadro's law states pressure, or at least the volume, decreases with the number of particles, but as we lower the number of gas particles in the container, I'm going to lower the pressure. So what I'm trying to do is, and I'll put the top back on and seal it here. What I'm going to try to do is take out the gas molecules. I'm going to try to lower the pressure above the liquid. We know the liquid right now is evaporating because it does have molecules that have enough energy to overcome the attractive forces between them. And we know it's evaporating, but at a low rate. And we're trying to get boiling here. We're trying to boil water at room temperature. You can read the thermometer is about 23 or so. Hard to read through the glass chamber, but it's about 23. And we're going to try to boil this water at room temperature, about 23 degrees Celsius, by lowering the atmospheric pressure. That's all I'm trying to do here. Because we know that boiling is when the atmospheric pressure upward, which is the gas molecules escaping into the gas phase, equal the atmospheric pressure pushing down. When those two forces are equal, we get boiling. So when you say the boiling point of water, it can be any temperature. So I'm trying to prove that. So let me turn on the vacuum pump, lower the pressure, and right now this water is evaporating. It is going from a liquid phase to a gas phase right now. We don't see it because you can't see steam, but it's not boiling because the atmospheric pressure is too large. So we're going to lower the atmospheric pressure right now. And I'm pulling out the gas molecules, and once I drive out all the gas molecules, there'll be less molecules to collide with the surface, less force pushing down the surface, and I should achieve a maximum rate of evaporation called boiling. So you can actually see it starting to happen now, and there's our boiling. Now I want you to take careful, look at the temperature of the system. It's actually falling a little bit. And you may say, well, why is the temperature dropping? We're boiling at 22 degrees Celsius, 21 degrees Celsius. Very interesting. How can we boil at 21 degrees Celsius? Because boiling is when the atmospheric pressure equals the vapor pressure. And at 21 degrees Celsius, we're producing a low amount of air pressure. Well, if I have low force or atmospheric pressure pushing down, we've got boiling. We look carefully, though, the temperature is dropping. The temperature is getting colder. The water is getting colder as it boils. Very strange. Okay? Now, why can that be? It's really just below 20 now. Well, remember, very important. Evaporation or boiling is an endothermic process. We're not applying any heat here. Where is the energy coming from to make this water boil? It's coming from with the water within. So the water is losing the molecules that are moving the fastest are leaving as gas molecules because of the lowered force or lowest atmospheric pressure. So therefore, the molecules that are left are the slower moving ones. That's why the temperature is dropping. If I had a stronger vacuum pump, and there's some good examples of this on YouTube, we could actually make this freeze. Okay? I'll shut this down, but you can see clearly the temperature drop. Why? Because we're losing the higher end molecules to the gas phase. Therefore, the slower numbers, the best analogy I can give you is that you have a class that has an average of 80 in the class. You take out your top performers, your top people, the people earning the 90s, and I pull them out of the class, what happens to the average? The average drops. And my friends, that's what's happening here. The average kinetic energy is dropping because the faster molecules are moving. Therefore, we have a colder water. So it's a pretty interesting phenomenon. Boiling water, and it's getting colder. Now, I'm going to stop this, increase the pressure, and maybe, just maybe, I can make this freeze. Because now I'm down to about 16 or 15 degrees Celsius. More than I expected. Okay, so I'm going to stop this now. All right, and we made water boil at 15 degrees Celsius. What I'm going to do now is I'm going to let the pressure back in and see what happens. Okay, I don't think I saw any freezing, but let's see if we can read that thermometer any better. Okay, so the energy that was used to boil, okay, is being used, and that got pretty cold. So if we look at our thermometer, we're still about 14 degrees Celsius. So we were at 23 and we're down to 14. That showed us how much energy the water lost to the evaporation. Remember, evaporation boiling is an endothermic process. The environment gets colder.
So in this video, if he were to put his hand in this water, obviously it wouldn't feel hot, even though it was just boiling. It would actually feel cool to the touch. So, after watching that video, I'd like you to go ahead and answer question 8 and 9. So we want to explain how the water boiled despite being below its normal boiling point. And you should use the following words in your explanation: vapor pressure, intermolecular forces, and atmospheric pressure. For question 9, here we have a label from a box of rice-a-roni here. And it says we have a longer cooking time at higher altitude. So think about how the temperature of the water is going to be whenever it's boiling at sea level versus at high altitude. So then why does it take more time to cook our food? Question 10 here is about crush the can demonstration. So we want to be able to explain what happens using the following words: liquid water, gaseous water, vacuum, and atmospheric pressure. So let's take a look at what's happening here. So before heating, we're going to add some liquid water to the can. So my brown particles here are representing air particles on the outside of the can, and my green is representing air particles on the inside of the can. So right now, the air on the outside of the can is pushing in equally as hard as the air inside of the can. So I'm going to go ahead and heat this now. So whenever I put this on a hot plate, notice that all the air particles that were in the can have been forced out by the boiling water vapor here. So we still have an equal pressure inside the can versus outside the can. those forces are still balanced. So now I'm going to take this can, which contains my water vapor, and I'm going to flip it upside down into some cold water. Now, when I do this, all of those air particles, or rather those water particles, are going to condense back into a liquid. So now there's no gas pushing out, but we still have the atmosphere pushing in. So this results in the can being crushed. So the next one that we have here is student in a plastic bag. So a student is placed in a plastic bag, not over their head so they can breathe. And then we use a vacuum cleaner to suck out all of the air in the bag. So we're going to use a vacuum cleaner here to suck out all the air in the bag. So this is going to cause the pressure of the atmosphere to suction the bag to the student. So you'll see that the pressure of the atmosphere is actually quite strong, but because we live in it all the time, we're used to it. So let's go ahead and watch this one.
Obviously, we don't want to do. Oh my God. Morgan, pay attention. I'm going to hand this to you. With one of your hands, you're going to wrap your hand around the end of the vacuum cleaner like this to try to prevent the bag. From being sucked up into the vacuum. All right. I would put the end of the vacuum somewhere like in front of you, like near where your belly button is, kind of. All right. Okay. Just make sure your shirt. You put your hand here. That will prevent the bag and your shirt from being sucked up into the vacuum. Okay. Ready? Got it? Yeah. Is your hand around the end of it, kind of, but not covering it completely? Yeah. Ainsley, you gotta create a better seal here. Sorry. Right. Oh my God.
Here, Ainsley, you want me to record?
Okay, Morgan, if you start to feel uncomfortable and you want me to stop, just say stop. Okay? All right. 5, 4, 3, 2, 1. Did you feel yourself being squeezed?
Yeah.
Yeah?
Oh,
That was
you popped it. Good job.
That was the pressure.
So bad.
So you want to explain why the student found it difficult to move. So use the following words in your explanation: vacuum and atmospheric pressure. So the last demonstration here is going to be balloon in the Erlenmeyer. So we're going to take some water into a flask and boil it, and then cover it up with a balloon. The balloon is going to fill with steam and blow up. Now the flask is going to be removed from the heat and allowed to cool, and that's going to cause the balloon to enter the Erlenmeyer. So to remove the balloon, we can place a straw alongside and blow some air into the flask, and that will cause the balloon to escape. So you have 2 questions to answer here. So explain why the balloon was forced in the bottle. So use the following words: temperature, expanding air, partial vacuum, and atmospheric pressure. So number 13, we can put a straw alongside the balloon and blow in air. Why does this make the balloon come out? So you should complete classwork 3. Again, our outcome was I can relate observable phenomena to the behavior of gases.